All right, let's start chapter 4 for Geology at Granite Community College. This is on igneous rocks. So, talk igneous rocks. First thing before we get into igneous rocks, you need to know about lava. Lava is liquid melted rock material. Here's a picture of it. The igneous rocks are the rocks that cool and solidify from said lava. If the lava is below the surface of the earth, we call it magma. Exact same stuff, just it's magma when it's down there, it's lava when it comes up. Magma / lava, I'll probably just use lava the majority of the time, have three main components: a liquid, a solid, and a volatile. The liquid is the melt or the liquid of the lava. The solids are the silicate materials that are crystallized or in rock form within the liquid of the lava. And beyond the liquids and the solids, you have the gases in the lava that we call volatiles. These are dissolved in the melt, H2O, CO2, SO2, things like those natures. They're called volatiles because they are volatile and they can go pop. Rocks formed from lava at the surface are called extrusive or volcanic rock. Extrusive, extrude, right? Leaves. If the rocks are formed from a magma that cooled or crystallized within the earth, we call that intrusive, inside intrusive, or plutonic rock. So the magma chamber would give you plutonic intrusive rocks, and the lava flow on top will give you extrusive volcanic rocks, as shown here. These famous picture, Mount Rushmore, are intrusive igneous rocks. These were carved out of the mountain, so the I believe this is, I can't remember what Mount Rushmore is made out of. That's embarrassing. The rocks that create Mount Rushmore, I think they're granite, maybe, I don't know, had to be chiseled out. So the actual rock that makes up the faces was not exposed to the surface. So that's the super basics of igneous rocks. Let's go into the fine details. Igneous rocks are classified in numerous ways. First way we're going to talk about is mineral composition. Beyond that, we also have texture, which is the size arrangement of the mineral grains. Here we have an example of a igneous rock that has lots of different colors in it. It has pinks, blacks, whites, grays, glassy parts, for example, and each of these individual parts of the rock have in and of themselves their own textures and their own mineral compositions. We talked about minerals last chapter. Nope, sorry, skipped ahead a bit there. There we go. The minerals in the rock vary widely depending on what type of rock you're talking about. That being said, igneous rocks are composed primarily of silicate materials. That should sound familiar from last chapter. This example here, we have dark silicates, named so because they are dark. Olivine, pyroxene, amphibole, biotite micas, augite, hornblends, all examples of dark silicates because they are silicates that are dark. As opposed to that, basaltic compositions have a lot of these dark silicates in them. I was a step ahead of my slides. I apologize. If you have a rock that has a lot of these dark silicates and calcium-rich feldspars inside of it, composing of it, we call that mafic. Dark rocks are what we tend to refer to as mafic rocks. Mafic coming from the magnesium and the iron, the ferrium, within the rock. Basaltic rocks are more dense than, say, granitic rocks, and as we'll soon find out, comprise what the ocean floor is mostly made of. There we go. If you don't have dark silicates, you have light silicates. Light silicates such as quartz, muscovite mica, and various feldspars are exactly what it sounds like: silicate minerals that are light in color. A lightly colored igneous rock is what's known as having granitic composition. Granite being an example of this. Basaltic compositions from basalt, granitic compositions from granite. Light-colored silicates we also tend to call felsic. The felsic comes from the feldspar and the silica in the composition. Again, right, as we said before, feldspar is a very common in light silicates, so felsic, feldspar. The majority of the continental crust, again, as we'll touch on later, is composed of these light-colored granitic felsic rocks. And again, saying it's light-colored, saying it's granitic, saying it's felsic, all essentially describing the same thing. If you don't have dark and you don't have light, you have intermediate or andesitic composition, as shown here with this diorite and this andesite. It is exactly as it sounds. Well, this don't look too dark. Oh, it's not too light either. Well, it's about between the two. It's intermediate. Finally, we have a fourth type of igneous rock, a less common type that's called ultramafic, beyond the mafic level of things. So if you start with the light-colored granites, you come down, we'll see a picture of this in a bit, to intermediates to mafics, below the mafics or the ultramafics, similar to ultraviolet on the EM spectrum scale. As I said, rare, high in magnesiums and irons, and peridot, as I believe how it's pronounced, is usually what you talk about when you talk about ultramafics. Not the only ultramafic, but that's kind of what you talk about when you see ultramafics. Here's that slide I was talking about before. This is to a geologist, this carries so much information, it's crazy. That being said, at a introductory geology level, the importance of this slide is it connects a bunch of different ideas. The top parts would be your rock types, your common rock types, and the compositions, the granitic, basaltic, etc. And at the bottom are different scales that produce these rocks. As you increase the temperature or decrease the potassium, etc., you get these different combinations and colors, textures of rocks. And what this is showing us is essentially, let's take one of these arrows at the bottom, let's take the temperature arrow at the bottom. As you increase the temperature, you darken the rock, right? The olivine, the pyroxene minerals show up in your basaltic and your ultramafic rocks because those go along with an increase in temperature. As temperature increases, you start losing your quartz. That's the relationship that's going on in this slide. That's what that means on a very simple level. And it's all wobbly woogly because these different minerals behave differently when you look at all the mixtures that you put into the soup. Pictures of examples of the rocks we're talking about. Okay. Igneous compositions. The silica content of crustal rocks ranges from low of 45% ultramafics to a high of 70% in felsic rocks. And this is for the crust, right? That's what we're talking about here. The silica content, as we've talked about, influences magma behavior. This is something that's kind of cool. The rocks that we find, as I said, as we talked about a lot in this class, the present is the key to the past, the idea of uniformitarianism, meaning what I'm looking at now, the way it got there, is probably very similar, if not to the same, as the way other rocks that are like this also got there. If this works for A, I have no reason to think it doesn't work for A on the other side of the world, right? So if we find a granite, we can assume this granite, this light-colored rock here, A, this granite, came from a magma that produces granite rock, right? And if we look at magma that looks like granite, that produces granite rock, we know something about the rock when it was still in a liquid form, when it's still a magma or a lava. Granitic magma, the magma that produces granites, tends to have a high silica content and be extremely viscous. Viscous is your resistance to flow. The more viscous something is, the less likely it is to come out of the bottle. Water is not viscous. Syrup is viscous. Basaltic magma, on the other side, the magma that produces this dark color, this gabbros, for example, on this picture, they have a very low silica count, again, showed here and showed here, right? The silica at the bottom, the top arrow is silica, SiO2. And these basaltic magmas have a more fluid-like. They flow faster. They crystallize at higher temperatures. You know something about the magma because you know something about the rock. So that's mineral, that's grain structure. Let's talk texture. Texture describes the overall appearance of a rock based on the size, shape, and orientation of the minerals and grains involved. Before I go further, I will also state all these descriptors technically work for all types of rocks and minerals, but they sort of function in a different manner depending on what you're talking about. Like the texture of an igneous rock and the texture of a sedimentary rock, technically you're talking about the same thing, but not 100%. So you'll see when we get there. It's fun. So what can affect the texture of a rock? What factors do you have in play here? Well, the dominant factor describing the crystal size, and again, if we look closely at these rocks, you can see the crystals I'm talking about here, right? That granite, lots and lots of dots on it. The gabbro, not so much, right? The dominant reason why one rock has lots of larger crystals, one rock does not, is how fast it cooled. If something cools at a very fast rate, you get smaller crystals because the crystals don't have enough time to form larger crystals, to meld together larger crystals by the time they solidify. So they all solidify very quickly and individually. The slower something solidifies, the more time it has to connect with the surrounding crystals and give you larger crystals, right? Beyond that, the viscosity, which is directly related to the SiO2 in the mineral, plays a part. And then finally, dissolved gases. If you have a volatile, an explosive, some trapped air that comes bursting out, that's going to play a factor. When we talk about textures, we have some definitions. The first one is fine grain, or aphanitic, I believe is how it's pronounced. My terminology pronunciations leave much to be desired. Fine grain is exactly what you think it is. It's fine grained. You look at this rock, you don't see a lot of crystals in it, right? You see some dots, some pokes here and there, but you don't see actual crystals in the classic way you think of as a crystal. They exist, they're just really tiny. This one, a lot more obvious crystals, right? You can see you can almost like see the geometry of the shapes of the crystals with your naked eye, not only by color, but even of crystals that are the same color, you can see the differences in them. If you held this rock in your hand, it'd be super, super noticeable. If you got a granite countertop, although it's probably not actually made of granite, but go look at it, you can see the individual crystals on the rock. You have what's known as porphyritic texture. These are a side category of texture. This happens when the crystals form at different temperatures and different cooling rates. Meaning, this example showed here, this phenocryst, this large crystal, formed slower than the outside mass, the black ground mass around it. Since these are of different materials, they cool at different rates, allowing you to form differently sized crystals within the same rock. And we'll get into why you have different stuff in the same rock as we go. And lastly, you have glassy texture, most commonly known as obsidian. You've probably seen obsidian at some point in your life. If you think the smaller the crystals, the faster the cooling, obsidian would come from really fast cooling, right? Because you can't see any crystals. It's glassy. It doesn't exist. That texture doesn't exhibit. Pyroclastic, yeah, I guess you could call this a texture. This basically comes from the fragments when a volcano explodes. You see all the stuff flying up in the air. That's pyroclastic debris. When it lands, if it stays as a rock and doesn't break up into sediment, you get pyroclastic texture. This is the light tuft, the breccia, things of that nature. And it's kind of whatever blew off the volcano, right? This isn't necessarily the lava and the magma formed. This is all the chunks, all the gases and stuff like that. So we've went over a couple of definitions. Let's talk about granite real quick. You look at this, what do you see? Well, I see grains. I see visible grains, right? I see lots of pinks and whites and stuff like that, and grays. Pinks and white rock, those are feldspars. We talked about those in the mineral section. Cool. You see granite lots of places. All right. Often associated with mountain building because it's a crustal rock. And to be honest, not every rock that you call a granite technically would qualify as a granite, but granite's just a good phrase to use to describe all these rocks. We call it granitic texture for a reason. All these are granites. They vary in color based on the magma that they came from, but they all share the key feature of the large grains. Rhyolite is the extrusive equivalent of a granite. Remember, as we talked about before, intrusive means the rock cooled below the surface of the earth. Extrusive means it came out as lava and then is cooled lava. So rhyolite would be the volcano that held the granite erupted, and the rhyolite is what cooled on the surface. Notice here, you don't have the same crystal size because it's cooled a lot faster because it was out on the earth, but you have very similar coloring. That whites, those pinks, that's what gives us a rhyolite, as shown here and here. So you have probably the same mineral composition, just things cooled faster, which again gives you those smaller grain sizes and textures. Picture Yellowstone. I believe this is not a rhyolite. That's why it's so white colored. Diorite. Here we're entering the intermediate section of the rocks, right? Notice we have large grains, coarse grains, which means it's probably a magma that didn't burst the surface, but we don't have necessarily a light or a dark. We instead have a combination of the two. We have light feldspars and dark hornblends. This combination gives us the particular diorite color that we're looking at. Andesite being the extrusive volcanic version of it. When is it rhyolite? When does the rhyolite stop and the andesite begin? Without going into the mineralogy of it, it's kind of hard to explain on a just looking at basis. But if it looks a bit darker than you think it should, you would call it an andesite. And then we get into gabbro. Gabbro is the intrusive dark grained rock. Notice you still have textures. And again, look at this. We'll compare this to the basalt. Look at, even though they're both basically all dark mineral, one of these has grains, one of these doesn't. Which of those two has grains? That one looks like, it almost has a plasticky look to it. Almost has like a bumpy look to it. That's basically smooth. Yeah, it's got some, punches in here and there, but it's very finely grained. This would be the difference between the two. If you live locally around GCC, either the campus Houghton or the one in Ironwood, I think, you're going to be used to basalt. Basalt is the rock that we walk around on up here in Michigan's Upper Peninsula. And peridot, again, somewhat uncommon. Essentially, if you look at a very dark black igneous rock and you see green, you probably have a peridot. Scoria is another igneous rock we can talk about. When you see scoria, well, you may be familiar with the pumice stone, the thing you scrape your foot with to get all that gross dead skin off of, right? Scoria is essentially an igneous rock that's got a lot of holes in it. It's got a lot of air pockets. Why? Well, because it probably flew out of the volcano, right? Obsidian, we already talked about that before. Pumice, this is what I was talking about, right? Scoria and pumice are very similar. Exception being that pumice is super, super, super light. Scoria is pretty light, but still majority rock. Take away a lot of that rock, you get a pumice. going deeper in the difference between them, yes, there is more to it than just lightness, but that's for a class that is more focused on igneous in this overview chapter here. Pyroclastic rocks, already talked about this. It's a repeat slide, so I won't go too much into it, but pyroclastic rocks such as tuffs and volcanic breccia exist. Sweet. So we talked about real quickly about lava versus magma. We talked about the rocks that come when the lava and magma harden. Where does the magma come from? Ah, that's an interesting question. Where does magma come from? We know it comes from below the ground. How far below the ground, and why does it come up? Well, magma is generally accepted as partially melted rocks. You get some rock, you get it hot enough and with enough pressure that the rock melts, maybe add some water to increase the slurry factor, and you get a magma. So, when I say temperature and pressure, I mean, as I said, temperature and pressure, right? Decreasing pressure plays a role in the origin of magma. As you increase the confining pressure, this causes an increase in rock melting temperature. Or vice versa, if you reduce the pressure, you lower the temperature required for something to melt. You ever boil water at different elevations, you know exactly what's going on here, right? This example here, we talked about this. This is a divergent plate boundary. As it's pulling apart, it's reducing the pressure on that rock, allowing the rock to melt at a lower temperature, allowing more magma to form. Cool. Heat obviously is an important part. You really can't melt rock without heat. As you get deeper in the earth, things get hotter, rocks melt. And then water can also play an important role because water causes rocks to melt at lower temperatures because water boils, right? Important for the oceanic lithosphere to send into the mantle because that's wet rock dropping down, causing it to melt, causing your volcanoes to form at these plate boundaries between continental and oceanic plates, giving you mountain ranges, right? As shown here. This slide should look familiar from last chapter because this stuff ties directly in. Why does that rock melt? Why? Well, because you have the moist isn't really the right word, but you have that water-rich rock being shoved out into the hotter atmosphere, and then these mountains are popping up, releasing pressure, allowing the rock to melt at a higher rate, giving you this magma that then rises through the cracks, looking for less pressure, because that's how that game is played, right? Giving you mountain building and volcanoes. A single volcano makes stewed lava exhibiting very different compositions. This is because the volcano is simply the place where the lava leaves. If you have rock coming down and melting that has different mineral components, different chemical components from before, you will get different lava. So it's pretty cool, right? Bowen's reaction series, again, one of those very complicated charts, goes a bit into explaining this process. What this chart is trying to explain, what this chart is trying to say, is the different minerals and different chemicals involved based on how hot the magma is. If you have olivine, for example, in your rock, in your magma, you know it came from a very high temperature because olivine will melt at those high temperatures. Biotite mica melts at lower temperatures. So if you have predominantly a biotite mica or an amphibole, you're going to get rock that melted at a lower temperature. This Bowen's reaction series is a lot more in depth to this, as usual, but hopefully that kind of follows a little bit. So during crystallization, the composition of the liquid portion of the magma continually changes. This could result in the removing of elements by earlier forming minerals or silica components becoming enriched in the process, etc., etc. This magma composition changes in arguably 3 different ways: magmatic differentiation, assimilation, and magma mixing. The first 2 may be kind of confusing. Hopefully the third one, I don't have to explain too much, right? Magmatic differentiation is shown here. Essentially, you start with a magma body. You start with a big bunch of boiling rock. The volcano erupts. Some of that lava escapes. Cool. Now what you have is not all the lava escaped, so you have some magma stuck down in that chamber, but it's surrounded by a different rock. So the hot magma is, instead of leaching off of that gray, that like brownish squiggly rock, is now stuck in and is sitting in and is taking the minerals out of that gray rock that's surrounding it, giving you a different magmatic formula, a magmatic recipe. So the second time this volcano erupts, it will produce a different lava, producing a different layer of igneous rock. Assimilation is essentially the process shown here, where the magma is pulling the, when I said it's pulling the different chemicals out of the rocks, it's pulling them via assimilation. You have the magma that's really hot, stirring around, vortexing around. It's going to pull some of the host rock, either melt it or take fractures of it into the magma, melt them down, add to the magma mixture. Magma mixing is when two magma bodies mix. Okay. So, most magma solidifies at depth in Earth. Not all magma erupts. In order for magma to erupt, you need to have a place for it to erupt. That doesn't happen as often as you would think, so most rocks are plutonic in origin. We classify those plutons, that magma that's still under the ground, as shown in these three examples, that magma down there. We classify the way we find those by their shape, being tabular or massive, as long as orientation and essentially what's crossing over. This diagram here shows all the various different igneous or internal structures we can find, right? Magma chamber, if the rock is cooled, such as those dark brown rocks with the lines on them, those are internal magma chambers that have cooled. We notice that the magma chamber on the left is pumping magma into what we call a laccolith. This essentially is like a pimple of magma pushing up the rock, making a hill. You have dikes and sills shown here, which are, we'll go a bit into later on, which are essentially like cracks in the bedrock that the magma has shot into and expanded, and the orientation of those, be them up, down, or flat, gives you dikes and sills. The pipe would be the pipe that the magma came through out of the volcano. If that solidifies, you get a pipe of magma, right? Here, as I said before, are the examples of dikes and sills. A sill is a tabular plutonic igneous deposit wherein it is parallel to the levels. So if you can imagine coming back here, if you have this rock that these lines of red that are jutting out, let's say to the left and right of the magma chamber, those are creating sills. The dike, on the other hand, cuts across the layers, so it doesn't go with the rock, it goes against it. As you can see here, again, look at where the lines are going, crossing through those layers, giving us different rocks. So if you look to the left here where it says sills, those arrows are pointing to the lines within the layers, and then the lines crossing through the layers are the dikes. Not a super important distinction if you're not getting deep in geology, but cool nonetheless, the fact that these layers can form in all these unique compositions. And going forward beyond that, a lot of the cool and interesting geology we see throughout the world comes from this process. Why do you have these random pokes of rock sticking out in, out west? Well, igneous activity, cracks, crevices, the lava's going to flow where it flows. Batholith, this is a lot of those magma chambers all hanging out together. When I said before about the laccolith making sort of a pimple, a batholith's a really big one, right? These batholiths will essentially bolster up, push up the surrounding rock. Igneous rock tends to be a lot harder to erode than, say, sedimentary. So as you can see here, going from B to C, the topsoil eroded away, and then what was left when it got deep enough were those plutons, were those magmas that couldn't erode away, giving you this batholith mountain range as shown in the picture. Igneous minerals form a lot of these basically all the time. You get your mineral resources, your ores, from these igneous processes via hydrothermal solutions. Hydrothermal solutions originate from hot metal-rich fluids and are remnants of late-stage magmatic processes. The ore deposits we have up here in the Q&R, if you're from around this area, are from hydrothermal veins. You get water flowing around. I mean, if you have ever drank well water, you know water can have a lot of minerals in it. Your pipes will, if you have galvanized steel pipes in your house, they get a lot of crust on them. Eventually you have to replace the pipes because the water, the minerals flowing through the pipes gunk up the pipes, right? That process is analogous to what's going on here. You have this water in the magma, water's flowing through these cracks in the rock, depositing this material, giving you your coppers, your irons, your bauxite, whatever your tin, whatever you are mining nowadays was deposited there by these hydrothermal deposits. Piece of copper, right? So the copper has the look that it does because the water that carries the copper ions, or actually probably just the copper, the atomic copper, flowed through rock that had cracks that look like this. So when we dig down, find that particular chunk of rock with those cracks, we find this piece of copper in it. So I think that's everything for this chapter. As I said before, I'm going to go through, let you look at these in case you want to try to answer them yourself. My suggestion when you're watching this video is just to pause it on the question, see if you can figure out the answer, and see if you were right, because I can. If you have any questions, feel free to ask them for your participation points. Or, as I said, you can always comment on the YouTube video.
I'm just wondering, when are the chapter 3 and chapter 4 questions due?